exceptional and good talk. It always happens when it is the case.
Okay, let's start, and sorry for the delay. Today we have Maciej Zgierski from Institute of Physics of Polish Academy of Science from Warsaw, and he will tell us about thermodynamics with a single object, which is called superconducting vortex. Please.
Thank you very much for inviting me here. Thank you for having me here today. So I am from Warsaw Institute of Physics, and I am part of division which is called MACTOP, and this was founded by Foundation for Polish Science to investigate interfacing magnetism and superconductivity with topological matter. And within MACTOP, I am leader of the group which is called CoolPhone. So I have also web page running under this name. So there you can find the recent presentations from our group and also our recent achievements. So today I will talk about just single vortex. This will be experimental work, but my talk somehow will be split into two parts. One will be devoted to nanothermometry at nanoscale. We are experts in nanothermometry and in fast time resolved nanometry. So we claim that we have that we are guys who can measure, who are the fastest in the nano world as far as the measurement of temperature is concerned. So we can measure the thermal transients in nanostructure with resolution approaching a single nanosecond, which gives us access to explore some thermal phenomena in transients which were not seen before for lack of suitable instruments. But we developed such tool, such device, which allows us to get access, and on basing on this device, we are also in position to propose operation of some pioneering new devices. And one such device I will show today. So first I will start with a teaser. I will, this is the main hero of today's talk. So first it looks very modest because this is device which is this polycrystalline aluminum which can be evaporated as a part of e-beam lithography procedure. So you can go to your lab and do it within few hours. So its complexity is very modest. It's a very simple device, but it exhibits very rich physics. So in fact, what I'm showing you here, these are two devices. This bridge is type of this is in superconducting state, this type of Josephson junction, and it shows very pronounced sensitivity of temperature. I will explain the protocol that we use to probe such bridge to obtain the knowledge of temperature at nanoscale. And then this box 1 by 1 micrometer, it is in this square we are able to capture vortices when the box is cooled across TC and above certain magnetic field. So we are able to capture just the single vortex, and then with this bridge we'll be able to sense this vortex. So in fact I'm showing you here both thermometer and the single vortex box, but this thermometer is necessary to read out the state of the box to see whether vortex is there or not, because as you will see the manipulation of the vortex will be dissipative, will lead to heating of the box. So we have on one hand we have thermometer, on the other we have vortex electronics, because when we talk about manipulation of the single vortex, we then can think about building some application, some functional devices based on this manipulation. This may involve some logical elements or some memory cells. So also towards the end of my talk, I will try to outline how such device may operate as a memory cell. So, okay, for those of you who are not, okay, maybe all of you are familiar, but this is how the superconducting vortex looks like. So the vortex is the topological object, but it means that it is you can't have in normal superconductor material half of the vortex or 1/4 of the vortex, but if it appears, it always appears as a object which looks like tornado of supercurrent. So it encircles its core. That you have here running supercurrent, and it collects exactly 2 pi of the superconducting phase, so that the phase must be single valued. So when you go from here around, it collects exactly 2 pi. And in the core of the vortex, you have no Cooper pairs, no these superconducting electrons, so the order parameter goes to 0, and it allows exactly one well-defined amount of magnetic flux to pass through the vortex cores, which is defined as flux quantum, which is h over 2e. So I will talk about these objects, and I will show you how to just capture one such object and do some interesting manipulation with it. So the physics of vortices was mainly investigated for big ensembles of them. So here you have, for example, niobium strips of width 10 micrometer, 100 micrometer, and these black dots are superconducting vortices. So they appear in superconducting structure as a energetic compromise between superconducting state, between Meister state, in which magnetic field lines of external field are fully expelled from the structure, and normal state in which the magnetic field fully penetrates the superconducting field. But for some intermediate field values, the nature chooses such, allows to penetrate the field through some quantized magnetic filament. So again, each such core of the vortex contains exactly one quantized amount of the magnetic flux, which is phi naught, which is flux quantum. Sorry? I think it's exactly one flux quantum. Yes, that is the point. Yes, that always it is this flux quantum, that always it because this arises from the calculating the phase around this strip. So then I think that this collection of 2 pi, it imposes this quantization condition. So from this point of view, we tell that the vortex is pure quantum object. But why I call it topological? Because as you move it, you can't distort it. I mean, it will be always looking the same. So it's kind of, you can't, it's there or it's not there. Yes. So okay. So this is from people tell that that is why it's kind of the quantum nature. This collection of 2 pi protects it against some deformation or annihilation of only a fraction of it. Yes. Here we have another. So this type of pictures are correlated with whole probe microscopy, which is sensitive to the local magnetic field. So here you sense higher magnetic field because of this, of this focusing of the magnetic field going through the core. Okay, and then people were able to investigate these vortices in big ensemble, in big numbers, but so there was called the branch of physics, which is called vortex matter. You can build some lattices out of these vortices. By the way, vortex was first postulated by Abrikosov in 50s. And so then this was object first predicted theoretically, and only then people were able to really observe it, and then were able to observe some triangular, hexagonal lattices. But to date, it was not what I will claim that we can really single out one such vortex and do some useful application or really study physics of a single vortex. So our idea is to harness single vortex for application. So first we need to define criteria for observation. So it must be sufficiently high field, but not too high, because then the material becomes normal. Then we want to take just one beast, and then we want to put it into cage and tame it to control. Yes, so more or less I will follow this chart flow to, I hope by the end of my talk you will be able to see how to extract single vortex and then play with it. So by the way, this is the biggest European mammal. It lives in Poland. But I mean, this one is Polish, and these are perhaps American bisons. So it's very similar species. So now this was kind of maybe okay, introduction to the physics of vortices to give the general motivation. But now I will make detour to nanothermometry, because as you will see afterwards, the way I sense vortex is based, in fact, on thermal physics. So the moving vortex will be source of dissipation, and this dissipation will be sensed by the thermometer. So now I will make kind of, yes, so my talk will consist of these two parts, which in the end should converge to the common should give you a common flavor. So now I will talk about this fast nanothermometry. So I would like to tell that this having a tool which allows you to monitor thermal signal, thermal transients, the thermal physics in rapid thermal transients would allows you to explore phenomena which were so far has been not observed so far, because simply there was no appropriate instruments. And as far as the electrical and magnetic studies are common, so we know people measure IV curves, okay, they send some microwaves, they do some reflectometry. These thermal investigations at nanoscales are at low temperature, especially in rapid transients, where somehow we're lagging behind the electrical counterpart. So I would like to tell that okay, that the thermal physics contains these thermal properties. They contain also a useful knowledge about your physical system, which you should know if you want to fully understand what is going on. So if you talk about, you need thermometer if you talk about calorimetry. So if you calorimeter is the device that measures the heat associated with a certain physical process. So this can be how much heat you need to heat something up or cool down, but this can be also heat of the first transition, but this can be also heat of some basic dissipation process. One such process I will explain, I will have opportunity to discuss here afterwards. But more generally, thermometry is a way to monitor in superconductor or also in metals the population of quasi-particles, because the temperature is a parameter in Fermi-Dirac distribution. So on one hand, you can look on your system from phenomenological, thermodynamical point of view, and then you can talk about just single parameter, this temperature. And if you know temperature, then you know the full distribution of states. But you can also adapt this more microscopic point of view when you talk about the evolution of the population of quasi-particles. You can look how they change, this population changes from one place to another, how it propagates. So in literature, you will find these two ways of investigating some relaxation of systems, energy relaxation. So one that can be through monitoring of temperature, how temperature relaxes, but some people, they just talk about relaxation of the quasi-particle population. So these are kind of two different viewpoints on the same problem in physics. So having thermometer gives us access to observe dissipation at nanoscale, and sometimes it can be very tiny dissipation which cannot really be observed by measuring the voltage drop, just by sourcing current and measuring voltage drop. And I will show, yes, this vortex physics that I will talk afterwards will be a good example. And also thermometry is necessary if we want to do quantum thermodynamics. Yes, so thermodynamics is, I have this down to earth definition. I'm experimental, so I have down to earth definition of quantum thermodynamics. So we talk about quantum thermodynamics when we investigate heat flows arising from manipulation of single particles. So this can be electrons, this can be phonons, this can be photons. So people measured, for example, heat transfer from one object to another mediated by only 3 modes of phonons. So there are such experiments. Or you can talk about absorption of single photon. Or you can talk about the heat transfer due to through single electron channel in single atomic contact. So then the electron transport current transport is only mediated by, say, 3 channels, and then you can also talk about the heat transfer through such 3 channels, which is also quantized. Then people use these concepts of quantum of thermal conductance. And for my talk, I would like to kind of invite a new actor to the skin of quantum thermodynamics. This will be a vortex. So we will treat vortex as a single particle, single manipulable particle. Of course, it's not particle because it consists of many electrons circulating, but since it has this robust topological nature, we'll be able to treat it as a particle. So we'll be able, within this field, to talk about the thermal consequences of playing with a vortex. Okay, so this is some general chart for if you are dealing with thermal physics at nanoscale, you should be conscious of the fact that electrons in general at low temperatures, they have different temperatures than phonons. So although they are in the same place spatially, because okay, phonons are vibrations of lattice and are vibrating ions, and you have electrons flying around, but electrons are strongly coupled between each other. Phonons are strongly coupled between others, but these two systems, they don't talk. They don't want to talk to each other as you lower the temperature. And it means if electrons are heated, they can exhibit much elevated temperature above phonons. So for example, you can keep your phonon at 300 milli-K, but electrons can be well at 600 milli-K. And then it takes some, there you have some thermal coupling, and like 2 coupled bodies, it takes some time before electrons may thermalize back to phonon temperature if they are not excited. So in addition, these hot electrons, they may of course diffuse to regions of lower temperature. They can absorb photons. So this is principle of the bolometer. They can emit photons. So this is principle of blackbody radiation. And phonons in the nanostructure, they are coupled to phonons in the substrate. So you have, if you define some metallic film of the top of substrate, dependently how well it's coupled to the substrate, here you can also have quite big temperature difference. So in the end, you talk about temperature of your phonons in metallic structure and temperature of phonons in your substrate. And phonons may propagate in substrate to remote locations, because in silicon substrate, they propagate ballistically. And then they may hit some remote nanostructure and heat up electrons in this nanostructure. So this is non-galvanic way of heat exchange among 2 nanostructures, which is very often neglected. So we can imagine that if you have 2 qubits, although they are galvanically completely isolated, still they can be coupled by this channel. And this is also, so if you have thermometer, you can study the dynamics of all these processes. And these processes were mainly investigated in steady states by assumption of some models. And from these models, you could then extract, you heat something and you check how much the temperature rises of electrons. And then by assuming what are your couplings here, then you can extract some dynamic thermal parameters. But it is not, but such studies are model dependent. And our ambition is to extract them directly. So we need to measure heat flows in the dynamic thermal transients in this nanosecond regime, because these nanoseconds are the appropriate time scale to see the relaxation, to really to get access to these dynamical thermal properties. So here is, okay, this is some example of, this is not my experiment, but I like this to show as a motivation for thermal studies at nanoscale. So this is flake of graphene. So you have some, topological structure. So you have these edge channels. So that in principle, current should propagate only around these edges. Yes. So you shouldn't have theoretically any backscattering, and there should be no resistance. But if you scan this flake with so-called squid on tip device, here you have like 20, 50 nanometers squid, which is sensitive both to magnetic field but also to temperature. So you scan this structure, and then you will find such rings. So it means that the temperature is not uniform along these edges. So in fact, if temperature is elevated, the color changes here. So you see, so it's a very accurate method, 1 millicalorie full scale, but you see some centers of dissipation. So immediately you may realize, this transport is really not, it's not the real life is not so easy as you would like it to have. So these edge states, they suffer from backscatterings, or there is some dissipation going here. Yes. So this is the example how, and you can't see it really with performing some electrical measurement across here, but so this gives you access at very nano scale. You see what is going on. Yes. So this is the example. How, although this is really not the time resolved technique, but I like it to show as a kind of to prove that these thermal studies are important. So my heart is closer with this experiment. This is the one that we did in Kulfon group some time ago. So here we investigate diffusion of quasi-particle in superconducting wire. So quasi-particle is the simplest excitation in superconductor. So it is not paired electrons. So if you have Cooper pairs, they can be excited, and then these not paired electrons, then having non-paired electrons, the more of them you have, the higher temperature of your superconductor is. So here the experiment is following. We have heater, copper heater here. It is also, this is same photo. And we send short 5 nanosecond pulse through heater. It, when we get Joule heating here, we create quasi-particles which then diffuse towards this superconducting wire, and then in superconducting wire they diffuse towards detector. Detector is 60 micrometers away from the heater. So this is the detector is our thermometer here. So this is the bridge, which is temperature sensitive. So we expect that after injection of quasi-particles, after some time, we should observe the rise of the signal here, because it takes for quasi-particles some time before they move here in diffusive motion, bouncing forth and back. But this is the diffusive process. So during first nanoseconds, you should not see. After excitation, you should see any signal, but then the signal should rise up, pick up to certain value, and then diminish. So what we observe in experiment, these are experimental diffusive profiles of this quasi-particle recorded at nanobridge. Indeed, we see for first 30, 40 nanoseconds no signal. And then we see increase of temperature at the bridge by roughly 10 milli-K. It picks up and go down. So from analyzing the position of the maximum, we can directly apply Einstein's Smoluchowski law of diffusion. We can directly read out the diffusion constant of these quasi-particles. So this is Einstein's Smoluchowski law. It relays the mean square displacement of these quasi-particles with the time of this arrival of this maximum. And so this is the way how we can directly read out this diffusive constant. And then as you increase temperature, you see that the signal that you obtain on the detector, it diminishes. It becomes smaller because less and less quasi-particle reaches reaches here the detector, and it is because they are consumed they emit phonons more efficiently. So the process that I showed you here is very strongly temperature dependent. So as we increase temperature, electrons can relax by emitting phonons more and more efficiently, and that is why we expect that as we increase temperature, we should not observe any quasi-particles if temperature is sufficiently high. Yes, so this I will talk in a moment. Yes. So okay, this is now I'm coming to this, what we will do. So this is the thermometer, this is bridge, polycrystalline aluminum, 30 nanometers thick, 60 nanometers wide here, 200 nanometers long, very simple structure. So we have grains of 30 nanometers. And now if you measure the IV curve of such a bridge, you will find that you will see the supercurrent branch, meaning no voltage, although current flows. So this is the appearance of superconducting state. But as you increase temperature, this supercurrent peak becomes smaller and smaller. So the critical current depends on temperature, and this is the principle. So, but we don't, but then the critical current, if you measure this critical current, it may, if you ramp up the current going through the bridge, it will spontaneously at some moment switch. We call it switching because it has abrupt character from superconducting state to normal state. So this is some threshold. The switching current is some threshold current at which is the highest current which can still be supercurrent in superconducting state, and above exceeding this current, bridge tells no, I can't keep it anymore, and then it switches to normal state, becomes overheated, and whole structure goes above TC. So all this here, you develop hotspot, and everything becomes overheated, goes much above TC. But now, how we measure this switching current? Because this is stochastic process of this switching. So in fact, what we do, we send many pulses, 10,000 pulses, say, and in response to each pulse, the bridge may switch, but it doesn't need to switch. So if current is sufficiently low, probing current, testing current of this amplitude in this pulse, it never switches. So then we talk that the probability for switching is 0, but if it is very high, it always switches, so probability is 1. But for somewhere in between, you have narrow range of currents where the switching is probabilistic. So this probability is just the number of switchings divided by the number of total pulses. So I like to call this analogy that this is like tossing a coin. So each time, and then you count number of heads, say. But this is electrical coin. Our bridge is electrical coin because we can tune the switching probability with the testing current. So if you apply some intermediate amplitude, you have 0.5. But if you apply slightly higher amplitude of this testing current, can be 0.6. So you can measure this S, we call it S curve. So this is probability dependence of the switching process on the testing current. And in fact, this is our main parameter. This switching current is temperature dependent. So look here. Here I increase the temperature of the fridge by in steps of 2 milli-K, and after each increment, I measured many times this probability. So each time to measure probability always assumes that you have to send many pulses. Yes, if I want to measure probability of obtaining head for a coin, then perhaps you have to throw it at least 100 times to tell me whether the coin is fair, and still there will be some statistical uncertainty given by binomial distribution. But if you do it 10,000 times, then the probability is really well estimated. So we measure, the strictly in theoretical terms, probability can be only measured if you send infinitely many pulses, yes? But what we measure is estimation for probability, yes? So if I send 10,000, I can, with very good accuracy, get estimation. And you see here, with measurement with 10,000 results in very small measuring error. This is very reproducible. And okay, so here, for theoreticians, it's difficult maybe to appreciate, but I don't know how many experimentalists is here, but you see I can stabilize fridge very well with accuracy of much better than 2 milli-K, and then measure this probability. And this is this gives me a lot of room to investigate very tiny changes in temperature but the process is okay, intricate in the sense that the main parameter always that we measured with the bridge is probability, and then probability is temperature dependent, so we need some calibration. Yes, always along the bridge, yes. So this is very good to think about, yes, this analogy here, this flipping. So this is what we do actually always too. So now, okay, I made this long detour to the thermometry, and now we are back at with vortex. So we are coming back to our single electron box and the device that I showed you in the beginning. So we have here now we want to trap and detect the vortex. So what we will do, we'll use set of 2 pulses. First pulse is, we call it reset pulse, so its intention is to apply sufficiently high current here, but this can be very short current lasting a few nanoseconds. But we need to overheat the box above TC. And when we overheat above TC, it is in normal state. Magnetic field lines are piercing uniformly the box. But then when box cools down inertially in sufficiently high magnetic field, it will trap spontaneously one magnetic flux quanta, one superconducting vortex. And then, so this is the intention of reset pulse. We may call it also annealing pulse. We can call also initialization pulse. But then, after it's trapped and the structure is cooled down to the base temperature, so Tc for aluminum is 1.3 K, K is Kelvin. So when it's cooled down to, say, we work at 400 milli-K, then we send this test pulse. And this test pulse will, dependently whether vortex is here or not, will lead to switching or not switching of the junction. So this is our way to get convinced there whether we trap something or not. At the moment, I'm just giving the idea, but we are going to the physics, why it is so. So let's take let's do some measurement of the switching current, which okay, we can consider that the switching current is very close to the critical current, and we defined it strictly as the one for which the switching probability is equal half, okay? So what we do, we adjust the testing pulse in such a way that with this bisection algorithm, this is implicit method, I send some train of pulses. I see that my bridge switched with probability 0.1, so then it means that I have to slightly increase the current. Then my bridge switches 0.9 with probability 0.9, then I know that I have to reduce it. And after 10 steps, I find the value which gives me this probability half. But I can do it very fast because one pulse lasts, one cycle here lasts 100 microseconds. Yes, so even if I have if it is 100 microseconds, I have 100 milliseconds. So in 1 second, I can obtain one value of probability. So after 10 repetitions, in 10 seconds, I can find the switching current which corresponds to the probability equal half. So what we do here, we take now double box. Okay, just I have some example, because first we started with double boxes, then we had only the single box, but this, okay. So what we do, we measure this switching current as a function of perpendicularly applied magnetic field. And you see first parabolic suppression of the switching current, but then but then at some point you see pronounced suppression, some big dip, and then as you still increase, you find more these dips. And now when you look at the Ginzburg-Landau simulation, so Ginzburg-Landau simulation of such boxes, it tells you that upon increasing magnetic field, you should be able to add single vortices each time you exceed certain threshold. So first you add just one vortex to one box, then one to each of the boxes. And in fact, here there's some double features. So first this is one vortex added, here is second, then there is this third box, and so on. But here what we see that this is the map of the order parameter. So black means that there are no Cooper pairs, and yellow means that you have superconducting states. So the vortex is the current is flowing around, yes. So this supercurrent flowing around the normal core. That is why it appears black here. So then, okay, here what is important that you see that these are dips. So you have huge suppression of the switching current. And I told you that the switching current is temperature dependent. So what is our interpretation that, and this is kind of well confirmed, that okay, so you see this is switching current careful as a function of temperature. So as we increase temperature, we have suppression of the current. So suppression is a sign of dissipation. So if you see such suppression at a given magnetic field, we conclude that during readout of the box, during trial to measure the switching current, we do some dissipation. So this dissipation is in fact expulsion of the vortex. And when the vortex is expelled, it creates quasi-particles. And production of quasi-particles means enhancement of the temperature. And this is observed as a switching current here, as a suppression of the switching current. And each time we cross the certain threshold, we add a new vortex. Okay, so we have this sensing of the vortex due to dissipation. I will develop this idea further, but this is just to give you a kind of a first impression of the detection. But now we could ask whether the places where new vortices are added are, if they really appear in these places where we expect them. So there is such prediction that vortex should first enter to the strip, superconducting strip, if the magnetic field threading the box is roughly flux quantum. So this is order of unity. So we have flux quantum phi naught divided by W squared. W is the width of the box. So if your density of a magnetic field is such that it corresponds to roughly phi naught threading the area of the box, then it is energetically favorable for the vortex to settle in the box for the first time. And this was some predictions from 90s, and then it was verified by Martinez for niobium lines. But we do it here for aluminum nanowires and these boxes. And you both in experiment in Ginzburg-Landau simulation, and you see that, okay, for boxes, it really, if we plot the first vortex entry field as a function of the inverse of the area of the box, it nicely falls on the straight line. So this kind of prediction, I mean, this kind of line can be considered as a calibration curve for it. So I mean that if you want to trap your vortex at a given magnetic field, you just need to take the geometrical size, and it works very well, yes? So then you can consider this a calibration curve, which will give you very quantitative knowledge at which field vortex enters to the box first time when the box is inertially cooled across TC. So it means that below these field vortices are not in the box when the box is cooled down, and above you should see them. Sorry? Yes. These are different sizes of the box. Okay. No. I blocked something. I will switch it off and on. Okay. Okay. So yes. So here you have the different. So we fabricated many boxes and with different sizes, and then okay, you have here these points, and also for wires. And okay, this is also very kind of instructive to look at from energetic point of view on such vortex trapped in the box. So here you have Gibbs free energy plotted as a function of x. X is coordinated plotted here along this direction. So you see that at low magnetic fields, there is no local minimum for vortex to sit inside the box. But as we increase field, as we cross the B0, the local minimum is established first time. And then when still we increase the B, this local minimum becomes global. And the vortex then is stable here in this local minimum or global, separated with so-called Bean-Livingston barriers from continuum. So this is, yes, Gibbs free energy landscape. And this is the first ingredient of this picture, is that the larger the field, the vortex is more trapped in the middle of the box. And there is this critical B0 field that which I displayed on the previous, in the previous slide, upon which it is possible to trap vortex. So you need this local minimum. And then second ingredient is that this landscape can be tilted with the current flowing through the box. So as you apply current here, you exert Lorentz force pushing the vortex to the side. So it means that from this energetic toy model, you can expect that if you apply sufficiently high current, you will be able to tilt the landscape to extent in which you will be able to push vortex out of the box. Okay, and now we are coming back to okay, this is the experiment now. So we have single box. We have this reset and testing pulse, and we measure switching current of the perpendicularly applied field. So you see parabolic suppression of the switching current at low fields, which is in fact the manifestation of the Meissner state. So you create some screening currents in the proximity of the bridge, and then it lowers the order parameter, so it affects the critical current of the bridge. But then at this B0, which well corresponds to this experimentally established knowledge and also to this criterion, you see that this dip, which is sign of huge dissipation in the system. So the presence, so from this moment on, we are able to trap the vortex, and as we increase fields, we still are able to see that, okay, we see the low value of the switching current. This is high value here, here is low. And then we come back from the low to high again, and this can be interpreted in terms of this energetic landscape, that vortex is so deeply trapped that perhaps we can't move it anymore. We can't do anything with it. So vortex is still there, but we can't really push it. So this switching current, this dissipation, comes from the fact that during testing pulse, which is used to measure the switching current, we expel the vortex, we create dissipation, and then we observe much lower value of the switching current than just before vortex entered. So, and then once we exceed the switching current of the bridge, the current is not strong enough to expel vortex. So before expulsion of the vortex, we switch the bridge, and then we can't really see the effect of the heating. So we have here now what we will do in the next slide. We'll try to separate these two functionalities, because I told you that with this pulse I'm able to read out the state of the bridge, but on the rising slope of this pulse I expel first vortex when I'm in this dip, and then the temperature of the box goes up, so I observe it as a suppressed value of the switching current. But now what I want to do, I want to expel the vortex, but without the switching of the bridge. So what we will do, we introduce one more pulse, which we will call Lorentz pulse. And as you see here, when I apply this Lorentz pulse before testing the bridge, and its value is not sufficiently chosen in the proper improper way, I'm able to extend the Meissner state. So what we see here now, I take the zoom of this part. If I take zoom of this dip, the red curve is here also, it is the same. And this red is measured without Lorentz pulse. But when I apply Lorentz pulse, I see that I can measure again the high value of the switching current. So the interpretation is following. Here I measure low value because I didn't apply Lorentz pulse, and during readout, before switching the bridge, I had to expel vortex. This led to dissipation. But if I'm applying this Lorentz pulse, I can expel the vortex, then system heats up, but I wait 40 microseconds, so it cools down. So then when I read the system, vortex is not there anymore, so I observe high value of the switching current. So I have two clearly distinguishable states. One is at the moment of testing without vortex, another is with vortex during test. And now what we can do, we can take cross-section here for a certain magnetic field and investigate how the switching current of the bridge changes with Lorentz pulse. So here you see that I have low value of the switching current if I don't apply Lorentz pulse, meaning that during testing, so there is no this pulse, and during testing I have to push out the vortex, I hit the box, and I observe the hot state of the bridge there. Then when I increase the Lorentz pulse, nothing happens, because Lorentz pulse is still too low to be able to push the vortex. So of course we expect that there is some threshold. And once I exceed this threshold, it's very sharp. I'm now able to expel the vortex, but not switch the bridge. And then when I expel the vortex, box of course heats up, but I wait, it cools down. And then when I measure the state of the box, it's in state without vortex, so I observe it as a high value of the switching current. So I have these two clearly distinguishable states. So now, this is some movie that we can. This is the processes that I was describing. So we pull down, we capture vortex inside the box, and now we start applying current flowing through the bridge. So we apply Lorentz force pushing vortex to the side. So first, vortex is slightly displaced from its central position, but we add more and more current and more displaced. So think in terms of this potential. We now tilt potential more and more and more, and local minimum becomes shallower and shallower, and at some point it disappears, and this is the moment when vortex escapes, okay? So this is the process that I was describing. So this we do with Lorentz pulse. So this is Ginzburg-Landau simulation, and Ginzburg-Landau simulation does not consider effect of dissipation. So after this vortex was expelled, we should see the massive suppression of the order parameter in the whole box, because when vortex moves in the box and gets expelled, it creates quasi-particles, so temperature rises. Okay, and this is now something which we call vortex stability diagram. So what we did here, in fact, we put this curve, okay? So you remember what it was. So this is at given fixed magnetic field, we measure switching current as a function of Lorentz pulse. So we try Lorentz pulse, we try to push the vortex. So we want to check how this changes with magnetic field. So what we do, okay, so here slow, high, low, high. So in fact, here I collect many such curves as the one as I showed in the previous slide. So you see here that for some, these fields are upside down. It may be confusing, sorry for this, but historically somehow I did it like that, and then we didn't change. But you see that for small fields, there is always, we observe high switching value of the switching current. It is not sensitive to Lorentz pulse. It is not sensitive because at these low fields, we are not able to capture the vortex. But once we cross this B0, we start to see vortex physics. And you see that, that the critical current, which is needed to expel the vortex, depends on the magnetic field. So this is this dashed line. So at lower fields, it's easier to expel the vortex. But then, as we increase the field, you need more current to expel it, yes? So remember that blue, low value of the switching current, is stayed with vortex during readout. The red one, high value of the switching current, is no vortex during readout. So if there is red current here, it means that we were able to expel the vortex with Lorentz pulse. So that is why it's, okay, now not here, and we see the high value of the switching current. So you see that this is consistent with this energetic landscape, that as we increase the magnetic field, the vortex is more strongly bound in this local minimum. That is why we need to apply larger expulsion current. Okay, so more on this, we published this in Science Advances, this manipulation, and okay, and now we are coming back to thermometry. So, okay, so the readout is thermal because we observe this suppression. But we want now to sit at this point 2, at this magnetic field. We apply this Lorentz pulse, and we want to see what happens in the box. This is this thermal process, which would be not possible to be observed by, okay, by some other techniques. We want to see what happens with quasi-particle just after vortex was expelled. So what we do, we trap vortex, we expel the vortex, and then sometime later, which we call delay, which we plot here as a horizontal axis, we measure the switching current of the bridge, okay? So just after we expelled, we created a lot of quasi-particles. They are flying everywhere. So we overheated the box by 250 milli-K with respect to bath temperature of 400 milli-K. And then, then the electrons, they cool inertially, mainly due to electron-phonon coupling process, which I depicted in the beginning. So they give up extra energy to phonons. And in the process of cooling down, they relax back to the phonon temperature with time scale of roughly 400 nanoseconds. So pay attention here that this is in logarithmic scale. So this is really state-of-the-art of measurement of the thermal transient, because we measure here we're really with resolution of single nanosecond. So we can, okay, we just change this delay with resolution of single nanosecond. And then we are able to see the process that completely disappears after 1 microsecond. So competitive schemes, they offer resolution at the level of maybe 1 microsecond or sub-microsecond, so they would not be able to see this trace. But here we have access. We see that, okay, this indeed well corresponds to the electron-phonon coupling. And then this 250 milli-K, knowing the heat capacity of aluminum, can be converted into energy, which is dissipated during vortex expulsion. So this is, okay, you multiply the temperature rise by heat capacity of the box, you get this number, 410 in minus 11, which is 2 electron volts. So this is roughly energy of 1 visible photon. So when we expel this vortex from nanoscopic box, it is as if we had absorbed a single visible photon. Of course, we don't absorb here any photon, but that's to give you energy scale. And then we may ask, what is this energy comes from? So in the picture of so actually this is this is maybe some of you will know. I would like also to know your opinion about it, because there are in fact different interpretations. So one is the viscous flow. In the picture of viscous flow, the vortex that is pushed with Lorentz force here to the side, it acts like a plane landing in forest, cutting all trees on the way. So it would mean that it destroys all Cooper pairs in this strip. And then you just need to count number of Cooper pairs in this strip. So you take the number of Cooper pairs. They are paired in energy interval around the delta, around the Fermi sea. You take the density of electron state at the Fermi sea and volume of the box, and this your number of quasi-particles that you have to create it in this strip. And then each quasi-particle must acquire this roughly the energy superconducting delta. So you need to destroy this Cooper pair, so you have to pay for each quasi-particle data. So if you take it together, there is no any fitting parameter here. It's quite surprising. You get this number. So it remains in very good qualitative. I don't claim here any quantitative agreement, because also this heat capacity is not quantitative. And also here, you know, these parameters should be also taken with some margin, but order of magnitude is proper. So it looks like really the process that we see is really related to the destruction of this Cooper pair. And now it's question to you. There is this viscous flow interpretation, which was put forward by Bardeen first in 60s after he published this BCS theory. But some people tell that movement of vortex in the box is not dissipative as long as vortex stays here. So in principle, I should be able to push this vortex here, but as long as it doesn't leave the box, I should see no dissipation. And dissipation only appears as a consequence of full expulsion of the vortex. So at the moment when it gets out from the box, the quasi-particles from its core get spilled all around the box. And in fact, in my experiment, because you saw that here when I plot, okay, you see. So in my experiment, the difference, either I should consider this volume of quasi-particles, because this is the volume from which the quasi-particles may spill when vortex leaves the box, or I should consider this strip. So this is factor of 2 or 3 difference. So within accuracy of my experiment, I'm not able to say which interpretation really is valid. So we will do more experiments. But I met some guys who tell that this is correct. So they are in favor of this dissipative, this viscous flow, but there are some which are in favor of this adiabatic movement. Okay, and this will be the last slide, because I told in the presentation, I told that this is thermodynamics and application. So application is that you see we can measure this probability of the vortex expulsion with the Lorentz pulse. So you see that for sufficiently low Lorentz pulse, I can never expel the vortex, but for sufficiently high, I always expel. So then the Lorentz pulse acts as a right pulse. So it changes the logical state of the box from 0 to 1. So we have 0 without vortex and 1 with vortex. So Lorentz pulse is our right pulse. And then readout is done with this testing pulse, and it checks the state of the box, whether it has vortex or it has no vortex. So if we take, you remember we had these 2 values of the switching current. When vortex was not present in the box, we had high value of the switching current. And when vortex was present, we had low value of the switching current. So if we take some testing current in between these 2, the bridge for sure will switch if the vortex is present in the box, because because switching now is here, but we test it with much higher current. So for sure it must switch. But if the box is empty, this current is not sufficient to switch the box. So it represents the principle of single shot readout. So it would mean that, so it means that we can really send one pulse to write the box, and we can send one pulse to read out its state. So this is the proof of concept of the memory cell. So, and also this shows some effects of superconducting diode, because here, if you look carefully, if you plot the central line, you will see that it's easier to expel the vortex to one side than to another. So it shows that this is something which we are investigating. Okay. So this is some additional thing that yes, so we are CoolPhone group. You may watch us at this page. So there are also some presentations from conferences which I try to record, and sometimes from such meetings now I'm also recording. So it is my good friend with whom I'm running CoolPhone group. Here is our PhD student. Here is our postdoc. We have good collaboration with Alexander Sravin from Aalto University from low temperature lab. And okay, and these are our papers. This is the most prominent one, which this is about these vortices, and here we have other papers are mainly devoted to this nanothermometry with nanosecond resolution, which we call switching thermometry. Yes, so thank you very much.
Questions?
Thank you for the talk. Could you put slide number 25? Yeah, what is this asymmetry between positive and negative Lorentz pulse? Just the vortex should move either to one side or to the other. Why the two is very different from when you go to from negative intensity to positive intensity?
You mean here, this vortex, yes?
Yeah, yeah.
Yes, so this is what people call this diode effect. I mean that when you break some symmetry, sometimes they refer to some time reversal symmetry. Okay, so here it is, if you plot. So on one side, you will see that to expel the vortex, this is the expulsion current needed to expel on one side, red and then black here, and to another works like this, yes? And then the kind of hypothesis that I have about it, but it is not yet checked, that it is due to some geometrical effect related to the fact that vortex is not fully placed centrally in the box. So so initially it's slightly, it sits somewhere, okay, not exactly in the center. And then when we bias it with the current, there is more flux and more current lines flowing on one side than another. And this gives some rise to asymmetry, which perhaps pushes it more strongly to one side than to another. You could imagine that if box was completely, okay, say that we put these electrodes here, you see? This one is at the bottom and this one also here at the bottom. So then when current flows here, it would be rather impossible to get rid of vortex to the here to in this up direction, because the current lines would flow here. So as you would expel the vortex, it would not fill current lines anymore. So it would stay here. But if you try to expel it on that side, you can attract the vortex and then expel it. So I think that, okay, we have such example, we have some preparation such example where leads are just connected here, and then we will see, then we should be able only to expel on one side. But this is at the moment hypothesis. But experimentally we see it. And this is for sure not a fake, because these borders, they mark the switching current of junction, so they are symmetric, as they should be. So only asymmetry that we measure is related to this expulsion current.
Can I just continue? And if you switch direction of magnetic field, it should also switch this asymmetry.
Yes. Yes.
Okay.
It's
Okay.
changed.
So it helps. Other questions?
So maybe this is very basic, but how relevant is the thickness of the sample in, let's say, in vertical? I mean, the vortex always moves like horizontally.
It's not so relevant because it is so thin that even if you increase it by factor of 2, it will not, because this thickness defines the parallel length in the structure. So in principle, the parallel length is the the most standard treatment is that you to get an idea how far the vortex current penetrates this London penetration depth. But then in dirty material, when the coherence length is short compared, yes, when you have this dirty limit coherence length, then instead of considering London penetration depth, we consider this effective London penetration depth. And then if you additionally narrow, thin down the structure, you have this parallel length. Then in London penetration depth in type 1 aluminum is 16 nanometers, which would tell that aluminum is type 1 superconductivity and should show no vortices. But then when you consider that you have dirty limit, then it becomes the psi becomes comparable with London penetration depth, and then it is kind of in the limit already. It may show type 2 superconductivity, and when you make it very thin, that is well deep in the second type superconductivity, because then this parallel length is more than 1 micrometer. So 1 micrometer scales like 1/d thickness of this film, and then it gives you the spatial extent of the currents flowing around the vortex.
Okay. And the samples, they are, what is the thickness in the
30 nanometers.
30 nanometers.
Yes. So this is also something that perhaps this could help us to give better idea. Yeah, we should also vary this thickness, because maybe we can expect different levels of dissipation.
Thank you.
Thank you for the great talk. What do you think about realizing auto engine with this? One can realize auto engine with the few vortexes, because what you need is hot thermalization and cold thermalization and the compression and the depression. So.
Okay. So you will have to propose me. Yeah, I have not been thinking.
So basically what you need is hot thermalization with the hot temperature and the thermalization with the cold temperature. And in between, you have to compress the vortexes and depress vortexes. And there should be work associated to the compression and depression. But I was thinking about it, but it confused me. What is the hot ensemble of the vortices? I don't know well. So.
Sorry, what is what?
The temperature, the ensemble of the vortices in the hot temperature. I don't know about it. So.
Okay. Yeah, because this I think all of your question also kind of prerequisite problem for your question is whether this movement of the vortex is adiabatic, or there are some thermal effects related to the manipulation, shifting vortex within the superconductor, or it is the question whether when pushing vortex from one side to another, already it leads to dissipation, or only process of expelling vortex out of the superconductor is a dissipation.
But can you change the size of the vortex, maybe?
I can change size of
by
the vortex
by changing magnetic field.
Changing the thickness. Yeah. But once in a given structure, it has the given size. But I can make, for example, 2 boxes, and I can push vortex from one box to another.
Okay.
And then I can try to do this type of games. Yes.
Yeah.
Yes. So instead of expelling it out to the continuum, I can try to expel it to another box, and then see the thermal consequence of such expulsion.
I see. Maybe it's possible then.
Yes. Yeah. And so, but if you have some idea how to make engine out of it, I am You would need to plot for me.
Okay, we can discuss further.
More questions?
Just a second comment. Just for me to understand, when you say that you have thermometry at the nanoscale, so here you have the scale of the length of the pulse, then you have the waiting time for the
Yes,
other
yes, yes.
current. What is this nanosecond referring to? Where do you identify the nanoscale, time scale of the temperature measurement?
Okay, good question. So, okay, I was speaking on you a bit. I mean, no, I will tell you what is the story with that. So, the point is that this method addresses perfectly repeatable thermal processes which can be restarted many times in the same initial conditions, because otherwise it is not single shot readout. This method gives you the opportunity to, okay, here it should be, yes. So we hit structure, we excite, and then sometime later we test. And the resolution is set by the duration of the testing pulse. But we measure probability. So because we measure probability, it means that we have applied this cycle, this sequence 10,000 times. So in fact, to obtain 1 point, say, now we excited and we want to see what happened 20 nanoseconds later. So I have to restart my system 10,000 times in this initial state, and then after each time, after 20 nanoseconds, I have to check I have to measure the probability. I mean, with 1 pulse, I will not measure probability, but I have to make a single toss of the coin, yes? And in the end, if I repeat this process 10,000 times, it lasts 1 second. But then I obtain 1 point, 20 nanoseconds after the excitation happened. But the way I probe it gives me the temperature just at this moment, at this very particular moment. So what I say that this is not single shot measurement, but this allows you to reconstruct that temperature profile in time scale. That is why it addresses perfectly repeatable thermal processes, because we measure the probability of something, yes? So measuring probability has only sense if you study all the time the same system, yes? I cannot measure if this pulse probes one system and then in next cycle it probes another system, then yet another, then I don't know what probability I measure. But if I'm able to restart my system always in the same initial condition, always I probe the same system. So in some sense, I have to probe over ensemble of many systems, yes?
And then the size is set by the length of the pulse that you are sending.
Yes, yes.
So if you send a shorter or a longer pulse, what does it have? What is set in the design?
Yes, so it's the
Pulse,
duration of this pulse.
that pulse duration is not exactly equal to the duration of the pulse that you sent the red one.
The red one is a heating pulse, so this can be okay. So you are limited here by the time resolution of your arbitrary waveform generator. So I have generator which has rising time of 2-3 nanoseconds. So in fact, this pulse, it is nominal definition. Oh, okay, so we are lucky now it's 6. But it has more Gaussian shape, and in fact you probe only with the top part of this. And I bought recently much faster generator which has the rising time of 150 picoseconds. So then I would be in principle able to claim the resolution of maybe 200 picoseconds, but then some other that I have not tried yet. Yes, but this is the.
So you use this blue talk and the 1 nanosecond.
Yes, it is for practical application. It's 1 nanosecond because 4 nanosecond is definition is in generator how you put it. But you can't. I mean, in practice, you can't deliver the pulses with infinitely sharp rising times. It's impossible. So always we talk in experiment about rising time and about rising edge and trailing edge. And for some commercial generators, which are maybe 10,000 for you that you can get for 10,000 euros, you can get the rising edge of 2-3 nanoseconds. If you pay 100,000 euros, then it's one of the magnitudes better. Yes.
Okay, yeah.
So in the end, we are limited. So in the end, the resolution of method is limited with amount of money that you have.
More questions?
Fundamentally, it's no.
No, it's fundamental limit, money. So more questions, or should we thank you one more, our speaker?
So you know.